Okay, so in the last video we talked about using light to identify the kind of material that is emitting that light, and that's a fundamental tool of astronomy. And now we'll talk a little bit about another fundamental tool, which is the Doppler effect, which allows us to use light to figure out how things are moving either towards us or away from us. So in this drawing, here is a source of light that's in motion. And if we think about it as not being in motion, then we sort of, let's maybe make a drawing. If we think of it as not being in motion, then we would have, here's the source of light, and it emits light, which is, we can think of it as a bunch of waves that propagate outward like this. And so you're an observer, you'll get a certain number of waves reaching you. They're traveling that way and so on, regardless of whether you're here or here, and so on. You'll always see the same frequency or wavelength of light, but that changes once the source starts to move. So if the source starts to move this way as it emits this, then you'll get a greater frequency of these waves, and that's what this drawing is trying to illustrate. So here the source is moving to the right, and so this observer gets more of these blue lines, more of the wave front, and greater frequency corresponds to bluer light, and the opposite happens for this observer because the source is moving away, so the light emitted this way reaches, these wave fronts reach this observer at a lower frequency, and therefore the light is redder. Whereas in this case, nothing special happens if you observe in this direction. So this gives you a sense of how this motion affects the wavelength of the light. And so we can tell the direction in which the object is moving. And in particular, we can tell how fast the object is moving along that direction. And so here's an image of the shifting of an emission line. Actually, this is an absorption line. Well, whether it's emission or absorption doesn't really matter. What you notice is that if the source is at rest, you get a line at some location, and if it instead moves, that line shifts one way or the other. So it'll shift to a greater frequency, smaller wavelength, and therefore it's more towards the blue if it's moving towards you along the line of sight, and the opposite if it's moving away from you. And we can imagine doing an experiment, figuring out exactly how much that shifts depending on the speed. And so we would end up coming up with the following expression. So we can imagine getting this from experiment. And so here is the figuring out the speed of the source. Right? We can imagine doing this experiment, and we observe some wavelength, and we know the wavelength at which the object was emitted, wavelength of emission, divided by the wavelength of emission, times the speed of light. This is the expression that we would come up with if we did some simple experiments with a source moving at speeds that are not too large, that are familiar with our everyday experience, let's say, using flashlights and things like that. So we could write this in terms of we could solve for the wavelength observed from this relationship above, and we would get the speed of the source. Or you could figure out at what wavelength to find the light if the source is moving at a certain speed v, lambda em over c plus lambda emitted That's the wavelength, and that is lambda emitted times v over c plus 1. And you might recognize this term in parentheses as the low velocity limit of a special relativistic expression that we saw in the special and general relativity course at the beginning of the course, because this expression is actually valid for low speeds, but not for speeds that are approaching the speed of light. We'll have to modify that expression.